Hello, my name is Carson Stewart. In this presentation, we'll focus on the material nylon, specifically with its use with high-speed sintering. The title of my paper is Materials for High-Speed Sintering. This paper can be found in the Cameras Journal, Volume 29, and was published in 2014. The specific scope for the study is to expand the number of processable materials for high-speed sintering manufacturing. High-speed sintering is a relatively new form of layer-by-layer, powder-formed base additive manufacturing process. This process can be broken down into a number of steps. The machine itself consists of two beds, a feed bed and a build bed. The feed bed is raised above the machine surface and the build bed lowered by the same amount. The first operation is to deposit a layer of powder. The carriage travels from one side of the machine to the other to transfer powder from the feed bed to the build bed. The carriage then travels in the opposite direction and deposits a radiation-absorbing material, also known as RAM. The purpose of the RAM is to absorb the radiation that is produced by an overpassing infrared lamp. The area of the powder that is covered by the RAM absorbs more energy than the area of powder that is not covered and heats up significantly, causing the covered area to sinter. Once the infrared lamp has made its pass, the process restarts, building layer by layer. The key question addressed in this journal is, can materials that are used for laser sintering also be used with high-speed sintering and retain the same laser sintering mechanical properties? Laser sintering is similar to high-speed sintering in that both processes require a powder that is able to flow at elevated temperatures. The amount of known material for high-speed sintering is limited, whereas nylon 12 is the standard feedstock material for this process. This journal tests two other common laser sintering feedstocks on the high-speed sintering and compares the mechanical properties. The two materials used were a filled nylon called Duraform HS T10 by 3D Systems and an elastomeric form of nylon called TPE 210S by ALM. Optimal process conditions for the laser sintering and high-speed sintering process were chosen such that the mechanical properties will be maximized. For the laser sintering process, previous studies were used to determine the laser power settings that would maximize the mechanical strength properties. For the high-speed sintering process, the build bed temp and the infrared lamp power were also optimized for maximum mechanical properties as well. Tensile test specimens were produced with both laser sintering and high-speed sintering methods. The ultimate tensile strength, elongation at break, and Young's modulus for each test specimen was characterized by a tensile test machine shown in the picture to the right. Key results for the study. The ultimate tensile strength and elongation at break for both processes for the Duraform HST10 were very similar in values. The high-speed sintering specimens shows a slightly reduced tensile strength but slightly increased elongation at break. The TPE 210S material showed more than 2 times elongation at break for the high-speed sintering method when compared to the laser sintering method. For the Young's modulus, the laser sintering method shown in blue produced a higher value than that of the high-speed sintering for the Duraform HST10 material. It was believed from the report that the nature of the material can affect the sintering process. Since Duraform HST10 is a filled material, it is believed that this may have affected the melt behavior and influenced the mechanical properties of the parts. For the TPE 210S, the difference in the Young's modulus for either process is negligible. Key conclusions from the research paper. It was shown that high-speed sintering is capable of processing laser sinter grade polymeric powders. Mechanical properties of the specimens produced by either processes were similar enough to confirm this. The journal also predicts that there may exist some other powders that high-speed sintering can process that laser sintering cannot. Moving forward, to improve the mechanical properties of laser sintering grade powders that are processed by high-speed sintering, the efficiency of the heat transfer between the RAM and the infrared lamp would have to be enhanced. I personally found this research paper to be very useful. As the paper suggests, little material development has been performed for high-speed sintering when compared to other established base additive manufacturing technologies. Further research could make high-speed sintering a frontrunner in the powder-based additive manufacturing technologies in the near future.